Morning, my YouTube viewers. It's Crystal here, and in this video what we're going to do is we're going to talk about hypothesis testing using R's inbuilt functions. So that's a great thing about R, is you can carry out hypothesis testing in R, and the reason why is because R is a statistical programming language written by programmers. So there's a lot of statistical functions inbuilt in R, so you don't need to import libraries, which is a contrast to Python, because Python is a general purpose language. And if you want to carry out hypothesis testing in Python, then what you need to import libraries such as SciPy or NumPy. And Python does actually have, I think, an inbuilt statistics library, but it doesn't have a lot of functionality in it. Maybe it only is for differential statistics. I'd have to have a good look at all of the functions within Python's inbuilt statistic library. But that isn't the case with R. You don't need to import any libraries in R. It's there for you already. And another thing is that a data scientist needs to be proficient in both R and Python. So they need to know how to use both languages. So that's why we're covering hypothesis testing in R. So hypothesis testing is a fundamental concept in statistics that enables researchers to make inferences about populations based on sample data. It involves formulating a null hypothesis and an alternate hypothesis, and then using statistical methods to determine whether the observed data provides sufficient evidence to reject the null hypothesis in favor of the alternate hypothesis. So we're going to talk about the first hypothesis test that we're making, and we're going to be using R's inbuilt function, the t.test function. So what we're going to do is we're going to create two sample groups. So this is going to be a two sample t-test. And the first thing we're going to do is we're going to set our seed. So when you set your seed, every time you run the program, the variables are going to be initialized to the same value. So you type set.seed brackets 1, 2, 3. So we define our variable group 1, which is R norm brackets 30, comma mean equals 5, comma SD equals 1. So group 1 is a randomly sampled normal distribution of 30 elements in it, or 30 samples, or 30 elements in it. The mean is 5, and the standard deviation is 1. And then so we have group 2, which is the same as group 1, except for the mean is 6. So the mean in group 1 is 5, and the mean in group 2 is 6. So then we perform our t-test. So t result becomes t.test brackets group 1, group 2, var.equal equals true. And then we present our t result. So this is the t result of the two sample t-test. So the sample is group 1 and group 2. Your t is negative 5.2098. Your degree of freedom is 58. Now your degree of freedom is calculated as the length of the first sample minus 1 plus the length of the second sample minus 1. So if both samples are 30, if both distributions or samples are 30 elements in them. So it's going to be 29 plus 29 equals 58. Your p-value is a really low p-value, 2.616 to the negative 6. That's really low. It's obviously less than 0.05. So that means that you are going to reject the null hypothesis because the p-value is less than 0.05. So the alternative hypothesis is true difference in mean is not equal to 0. So you've rejected the null hypothesis and you're going to accept the alternative hypothesis because the p-value is less than 0.05. It gives you your confidence intervals. So negative 1.69 to negative 0.75. So your confidence intervals are negative numbers. And since your confidence intervals are negative numbers, this indicates that group B is greater than group A. And then you have your sample estimates. So mean of X is 4.95 and mean of Y is 6.17. So X is going to be group A and Y is going to be group B. So you see the mean of group A is 4.95 and the mean of group B is 6.17. So again, that also shows you that group B is greater than group A. So we come back to the code and we're going to plot it in a box plot. So box plot brackets group 1 comma group 2 names equals you're going to create a vector of C brackets group 1 comma group 2 color equals you're going to create another vector C brackets light blue comma light green. Main is the title, it's to sample t-test, and Y-lab is your label on your y-axis, which is your values. Then we're going to add the means. So points, we're going to put points on the graph. Brackets C, we're going to add another vector, 1, 2, C, brackets mean of group 1 and mean of group 2. PCH, that's the size of the point, equals 19. Color equals red. CEX equals 1.5. And then we're going to add the t-test annotation. So we're going to put some text in there. So text brackets X equals 1.5, comma, Y equals max, brackets C, brackets group 1, comma, group 2, plus 0.2, labels equals paste 0, and paste is sort of like a print command. Brackets T equals the round of the T result to the second digit, and the next line, and signif is the p-value rounded to the third digit. So we run the program, and then when you run the program, this is the chart that is being created. So you've got group 1 has a mean of about 5, and group 2 has a mean of about 6. And you can see that in the red dot in the chart. And then we've created 2 box plots. You've got a box plot for group A and a box plot for group B. And then so you've got your outliers. So you've got your outliers. So you've got your minimum and maximum values on Q0 and Q4. And then you've got Q1 and Q2 and then Q3. So the mean on group 1 is pretty much sitting on Q2. And the mean on group 2 is slightly above Q2. So that just shows you the box plot of this t-test. So you can see the t-test and you can visually see that group 2 is got a greater mean than group 1. So now what we're going to do is we're going to carry out a hypothesis test using the chisq.test function. And so the first thing we want to do is we're going to create a contingency table. So the example data is going to be group A, B versus a preference of yes, no. So we create our data matrix. So data matrix becomes matrix brackets C, and we're going to create a matrix. So 30, 10, 20, 25 brackets, the number of rows is going to be 2, and then the by row is true. The column names of the data matrix become C brackets yes, no. So you've got 2 columns, one column being yes, one column being no. And the row names of data matrix become C brackets. Again, we're creating a matrix. Group A, group B. So the rows of this matrix are going to be group A, group B. And then we're going to print the data matrix. So we're going to come so this is our data matrix that we've created. So you can see you've got 2 rows being yes, no, and so 2 columns being yes, no, and 2 rows being group A and group B. And you can see that you've got the data in the rows and columns. So now what we're going to do is we're going to perform the chi-square-test. Chi result becomes chisq.test brackets data matrix. So you're doing your chi-square test on your data matrix, and then we're going to print the results of the chi-square result. So these are the results. The Pearson's chi-square test with Yates continuity correction. So your data is your data matrix. Your x squared or chi-squared is 6.9499. Your degree of freedom is 1. Now your degree of freedom is calculated as the length of the matrix minus 1. So the length of the matrix is 2, and 2 minus 1 is 1. So you have 1 degree of freedom. Your p-value is 0.008382. So your p-value is going to be less than 0.05. So that means you're going to reject the null hypothesis. And so basically what happens is the null hypothesis is there's no difference, no significant difference between group 1 and group 2. And the alternate hypothesis is there is a significant difference between group 1 and group 2. So if you reject the null hypothesis in favor of the alternate hypothesis, then what the outcome of the result is there is a significant difference between group 1 and group 2. And these hypothesis tests are useful because what they do is they help you give a scientific backing to your result rather than just using gut feel or using your opinion or using what you like. You've got scientific evidence to prove why you are selecting a certain group for your test. So now we're going to plot the observed counts. Bar plot brackets data matrix is your data. Beside equals true. Color equals, we're going to create a vector being sky blue and light green. The main is the title, is observed counts by group. Y lab is your label on your y-axis, which is count. And your legend is your row names and your data matrix. And so we're going to add an annotation, which means we're going to add some text to the chart, to the bar plot, brackets paste, brackets chi-square, df, and p. So what it's going to do, it's going to show you your chi-square value rounded to 2 values. It's going to show your degree of freedom, which is your chi-result, $ parameter, and it's going to show you your p-value, which is your chi-result, $ value. And then your chi-square is your chi-result, $ statistic. So your outcome of your chi-result gives you your statistic, your parameter, and your p-value. And then side equals 3, line equals 0.5. So we come over here and we're going to look at the chart that has been created. So you can see the chart has been created. And so your chi-square statistic is 6.95, your degree of freedom is 1, and your p-value is 0.00838. And so what you're getting is you're getting a visual representation of the fact that Group A is significantly different from Group B. And now we've got another chart that we can plot. The combined and observed. If I can just get it. So expected becomes chi-result, $ expected. And pair brackets MF row equals another vector, brackets 1, 2. Then you have a first bar plot, brackets data matrix, comma, the side equals true, color equals a vector of sky blue and light green. Main is the title, it's observed counts, and white lab is the label on the y-axis, is count. And then now you have another bar plot, which is expected because we've already calculated what expected is. The side equals true, color equals a vector of orange and pink, main equals the label, which is expected counts, and y lab, which is the label on your y-axis, as counts. So we come back here, and this is the chart that has been created. So you've got your observed counts and you've got your expected counts. So when you look at your observed counts, you can see that Group A is significantly different from Group B. And when you look at your expected counts, you can also see that Group A is significantly different from Group B. So that's just another way that you can create a chart to show your results of the hypothesis test. And you can use this chart in a presentation to show people that you want to give information to the results of the hypothesis test. So now what we're going to do is we're going to use R's prop.test function. And the prop.test function performs a hypothesis test for one or more population proportions using chi-square test for proportions. This function is used when the researcher wants to compare proportions rather than means. So basically, you've got your population, and then when you have your population, you can take a sample from the population. So normally, you're actually dealing with samples. But in this case, you're dealing with a high population. So the population is all of the data. So in this exercise, we're going to be dealing with a population instead of a sample. And then so populations have proportions and samples have something else, statistics. So the first thing we're going to do is we're going to create 2 sample data. So, and this is going to be another chi-square test. So success becomes a vector of 45 and 30. So you're going to have successes in Group A and Group B. And totals becomes a vector of 100 and 100. So those are going to be your sample sizes. So we're going to run the proportion test. Test result becomes prop.test brackets successes, comma, totals. And then we're going to print our test result. So this is the test result. 2 sample tests for equality of proportions with the continuity correction. So your data is success out of totals. Your chi-squared is 4.1813. Your DF, your degree of freedom, is 1. And your p-value is 0.0408. So your chi-squared is your test statistic. And your degree of freedom is calculated as the length of the data set, which is 2 minus 1, which gives you 1. And your p-value is calculated using a mathematical formula of 0.04, where your p-value is less than the standard of 0.05. So the null hypothesis would be that there's no significant difference between the 2 samples. And the alternate hypothesis is there is a significant difference between the 2 samples. And then so basically, if the p-value is greater than 0.05 or greater than or equal to 0.05, then you would fail to reject the null hypothesis. But in this instance, since the null hypothesis is less than 0.05, then you have to reject the null hypothesis in favor of the alternate hypothesis. So we're selecting the alternate hypothesis. There is a significant difference between the 2 samples. And then so we've got our 95% confidence interval, which is 007 to 0.007 to 0.029. And then your sample estimates of prop 1 is 0.45 and prop 2 is 30. So now we're going to create a bar plot of our results. So BP becomes bar plot brackets props, comma, names.arg equals a vector of group A and group B. Color is a vector of sky blue and light green. Wide limit, that means your lower and your upper limits, is a vector of 0, comma, max props plus 0.1. Main is your title, is 2 sample proportion test. And your Y lab is your label on your y-axis, which is proportion. So we're going to add some labels above the bars. So we're going to put some text in there. Text brackets BP, comma, props plus 0.03, comma, labels equals round, brackets props, comma, 2, comma, CEX equals 1.2. Then we're going to add some annotation, add some more text, and brackets paste 0, brackets chi-squared, which is surrounded test result $ statistic to 2 points, and P, which is the significant brackets test result $ p-value rounded to 3 points, side equals 3, line equals 0.5. So we run the program, and when you run the program, you can see this is what we've come up with. We've come up with a 2 sample proportion test with a chi-square of 4.18 and a p-value of 0.409. And then we've got a bar chart to illustrate it. So group A goes up to 0.45 and group B goes up to 0.3. So you can see in this bar chart that there is a significant difference between group A and group B. So the next thing we're going to do is we're going to talk about manual permutations. So manual permutation test is a hypothesis testing method where the test statistic is computed for every possible rearrangement, that's your permutation, by hand or with a simple code to build the sampling distribution without relying on normality, t.test, or any parametric assumptions. It is one of the most intuitive, assumption-free ways to test whether two groups differ. So we're going to create a program to perform a manual permutation. First thing we're going to do is we're going to set the seed. So whenever you set the seed, every time you run the program, the variables are going to set up to initialize to the same values. So we're going to type set.seed brackets 1, 2, 3. So we're going to create the two groups. So A becomes R norm brackets 20, mean equals 5, ST equals 1. So what that means is you have a randomly sampled normal distribution that's going to have 20 elements in it. The mean is 5 and the standard deviation is 1. And then B is the same. It's going to be a randomly sampled normal distribution with 20 elements in it with a mean of 6 and a standard deviation of 1. So we're going to observe the difference in means. So obsdiff becomes mean A minus mean B. So you're going to take mean A minus mean B. So we're going to pull the data. So pull becomes C, A, and B. So that's a vector with A and B in it. And we're going to run the permutation test. So in perm becomes 5,000. Perm stats becomes numeric brackets in perm. So basically what you're doing is you're creating a blank vector that is a numeric type, and it's going to have 5,000 placeholders in it. So you're going to have 5,000 placeholders in this blank numeric vector. And then we're going to create a for loop for I and 1 to n perm. So that's I and 1 to 5,000. And in this for loop, you're going to shuffle it. Shuffle becomes sample brackets pull. And so that's your permute values. And A star becomes shuffle square brackets 1 to length of A. So length of A is going to be, I think, 20. So that's going to be your first group. And B star becomes shuffle square brackets length of A plus 1 to length of pull. So that's going to be length of A. So that's 21 to 40 because A has 20 elements in it and B has 20 elements in it. So star A is going to shuffle from 1 to 20, and then star B is going to shuffle from 21 to 40. So that's how it shuffles it. And then you're going to perm stats I, because remember you have in perm is 5,000. So I is the number of iterations that the for loop goes through. And so I is going to be that placement. And so I can be anywhere from 1 to 5,000. But perm stats is that placement, becomes mean star A minus mean star B. So what you're going to do is you're going to take the mean of star A and you're going to subtract the mean of star B from it. And then so that particular value that you come up with is going to be put in perm stats I. And then so what you're going to do is you're going to iterate through that 5,000 times. So 5,000 times you're going to have perm stat with a little I in it and the number of the iteration and the mean of star A minus the mean of star B 5,000 times. So that's how a for loop works. So we're going to compute the permutation p-value. So p-value becomes mean brackets ABS, that's absolute value, brackets perm stat greater than or equal to abs, that's the absolute value of obs diff. So, so we've got our mean of the absolute value of the perm stat. So we created the perm stat, and let's see what we've got here for. And we've already created our obs diff is the mean A minus the mean B, and the perm stats is the mean of the samples, A minus B. So, and then we're going to calculate our p-value. So we're going to come over here and we're going to look at our p-value. And your p-value is 0.0086. So your p-value is less than 0.05. Your significance level, which is normally what they use, 0.05. So the null hypothesis is that there's no significant difference between the two samples. And the alternate hypothesis is there is a significant difference between the two samples. And since the p-value is less than 0.05, then you're going to reject the null hypothesis in favor of the alternate hypothesis, which tells you that there is a significant difference between the two samples. So now we're going to plot the permutation distribution, and we're going to do it in a histogram. So hist brackets perm stats, and perm stats is the sampled mean, A star minus B star. You're going to have 30 breaks. Color is light blue. Main is your title, is permutation distribution of difference in means. X is the label on your x-axis, is the difference in means. So we're going to add an observed statistic. So you're going to add your AB line, brackets V means it's a vertical line, equals obs difference, comma, color equals red, comma, line width equals 2. So we already calculated our obs difference at the beginning of the program. At the very beginning, when it said the difference between mean A and mean B. And your max is hist, brackets perm stats, brackets plot equals false, $ counts, labels equals paste 0, observed, and it's rounded to the obs diff, rounded to 3 points, and pos equals 4, color equals red. And then so we run it, and this is the histogram that we've come up with. So this histogram that we have come up with, is a normal distribution, which is not surprising considering the fact that the data that we used was a randomly sampled normal distribution. And so you can see that the difference between A minus B is, I think it's 0.8 or 0.7.5 or something like that. So you can see that the difference between point A and point B is not anywhere near the mean of the normal distribution. So we say that the obs difference is what we calculated at the beginning of the program. Is the mean of A minus the mean of B. And so you can see the obs difference in that diagram, or in that chart, and you can see it's not anywhere close to being normal, the mean. So now what we're going to do is, since we've been talking about hypothesis test, and now what we're going to do is we're going to perform a sample hypothesis test report, and we're going to do this using a t-test. And I decided to use a t-test because a t-test is easier to use than a chi-square test, but I could have used a chi-square test. But I just decided to use a t-test since it's easier to use. And then we're going to go through the steps of how to perform a sample hypothesis test, which, if you're going to be performing a hypothesis test and presenting it to other people, you need to be able to go through the steps on how to do that. So the first thing that we're going to do is we're going to define our research question. And the research question in this instance is do mean values differ between group A and group B? And then the second step is we're going to define our data summary. And so the data summary is the study collected 2 independent samples. And so we're going to create our own data, but when you perform your test, you're going to get your data from another means. So we're going to create our own data. And so in order to do that, we're going to set the seed. So every time you run the program, the variables are going to initialize to the same values. So group A becomes our norm, brackets 30, comma, mean equals 5, comma, SG equals 1. So that means you've got a randomly sampled normal distribution of 30 elements in it with a mean of 5 and a standard deviation of 1. In group B, you've got the same thing, but you have a mean of 6 and a standard deviation of 1 as well. And then so now we're going to use the cat function to print the mean of group A and the mean of group B. And so basically, cat function is like a print command, but it allows you to put text and variables in the command. So we're going to come over here. We're going to find our means. So your mean group A is 4.95, which is very close to 5. And mean of group B is 6.17, which is very close to 6, because we've already created our data for this example, giving you a mean of 5 and for group A and a mean of 6 for group B. So you notice that the means are very close. So now number 3 is we're going to define our hypothesis. So I'm just going to say right here, define our hypothesis. So the null hypothesis, which is H0, is mean A equals mean group A equals mean group B. And the alternate hypothesis, which is HA, or it can also be written as H1, is the mean of group A is not equal to the mean of group B. And then so now we're going to perform our statistical test. So t.test becomes t.test. So sorry, test result becomes t.test brackets group A, group B. So that's your test result. And then number 5 is we're going to have the test output, and which is going to be test result. So we come over here to the bottom of the cell, and so you get your test result. Welsh to sample t-test. Data is group A and group B. T statistic is neg 5.2098. Your degree of freedom is 56.559. And p-value is 2.755 to the negative 6. Okay, so your degree of freedom, if you're normally, is going to be the length of sample 1 minus the length of sample A minus 1 plus the length of sample B minus 1. So here, when we created our samples, we had the length of group A and the length of group B being 30. So if you were calculating it yourself, you might say, oh, well, 29 plus 29 is 58. But the computer calculated this, and they used a formula to calculate it. So they came up with a degree of freedom of 56.559, which is close to 58. And obviously, since scientists made this program, then you have to go with the formula that the scientists have put in the programming language. Now, the p-value of 2.755 to the negative 6, that's definitely lower than 0.05. And so since it's lower than 0.05, then you're going to have to reject the null hypothesis in favor of the alternate hypothesis. And so the alternate hypothesis is a true difference in means is not equal to 0. So the 95% confidence interval is negative 1.6 to negative 0.75. And then the sample estimates of mean of group A is 4.9 and mean of group B is 6.17, which is what we've already calculated. So that's very close to the means that we selected of 5 and 6. So now what we're going to do is we're going to actually interpret the test. So number 1, your t statistic is negative 5.2098 with 5, 6, 7, I made a mistake on that, with 5, 6 degrees of freedom. Your p-value is 2.755 to the negative 6, being below, sorry, my typing's not that good, the 0.05 significance level. A 95% confidence interval for the difference in means of A minus B is entirely negative, which indicates that Group A's means is less than Group B's means. Because the p-value is small, the null hypothesis is rejected. So if the p-value is below 0.05, you're going to reject the null hypothesis in favor of the alternate hypothesis. So that means that there is a significant difference between Group A and Group B. And we come back over here to our null hypothesis, define our hypothesis. So you can see the null hypothesis is Group A equals Group B. The mean of Group A equals the mean of Group B, which is the same as there's no significant difference between the mean of Group A and Group B. And then the alternate hypothesis is the mean of Group A is not equal to the mean of Group B, which means there is a significant difference between the mean of Group A and the mean of Group B. So we're going to come to our conclusion. There is strong statistical evidence that the mean of Group A is different from the mean of Group B. Based on the sample data, Group B has a significantly higher mean value than Group A. So basically that is how you perform a hypothesis test. And you can perform a hypothesis test using any one of the functions in R. And I just selected the t-test because I thought, well, it's going to be easier to do a t-test than it is going to be to do a chi-square test. Because if I did a chi-square test, I would have to create a matrix. And I thought, well, we'll just start out easy. So that concludes this video on studying hypothesis test in R. I hope that you got something out of the video. The next video, we will be making more statistical topics, and I hope that you decide to watch it, and I hope that it helps you in your statistical studies and statistical career in R. So thank you for watching.